level encryption before, and that includes like storing the ciphertext along with the hash keys and stuff in the column itself. I was on Rails, by the way, so that that obviously adds compute while reading and storing data, right? So that also got me curious about.
Okay, so we are live now on this AMA. Thanks to those who've been waiting on YouTube for joining the AMA. I was at the Generative AI Roundtable yesterday, and there was a big discussion going on about how generative AI is going to completely diminish the need for engineers. And then somebody said, "But what about SQL queries?" So here we are at today's AMA. Pretty much serendipity. But the reason for this AMA really was Chinmay's talk at the SRE conference about all the war stories that he's dealt with SQL. And it's like, SQL is like evergreen. And so why aren't we talking about it? And Swan has, of course, been missing because he's in greener pastures. So we said, okay, let's make this opportunity right now to get back Swan and Aditya and Chinmay in one room and to discuss. Everything that you like about SQL and everything that you don't like about SQL. And so the format is free flowing today, and the idea is that you can ask your questions, preferably ask your questions on comments or on Zoom. And for those watching on YouTube, you can put your questions. The animation is picking it up from there. With that, I'm going to hand it over to the folks who are here to geek out, and I hope everybody has a good session. Thank you.
So, cool. Are there Animesh, like I know you've been collating questions, so maybe we can start with some of the questions that have already come in and just see where like the discussion organically leads.
Hmm.
And let's say if not a lot of questions come in, then maybe Aditya, Chinmay, we can just discuss like general good practices, schema design, data integrity, performance, etc. Does that sound like a reasonable agenda?
Yes.
Sounds good.
So I guess we can start with the question that I had uh, asked on the Discord and stuff. Uh, I think that should be okay, right?
Yep.
So just
Sorry.
to reiterate, uh, I wanted to know what might be a good way to model hierarchical data. Like, let's say you're on an organization, you're like mapping your org structure, like modeling your org structure in any RDBMS or something. What might be a good way to do that? Usually, people just add a table and a parent ID reference to the table itself, but maybe that can cause some performance issues when you're developing the recursive query for reading all those records, right? So, does anyone have any ideas around that? Like,
Chinmay, you want to take that up? Like,
So I haven't used databases, especially Postgres or any relational database for this kind of use case. You can do that easily with a small kind of graph, I believe. There was one article and stuff that I read about storing, the people graph, like friend graph in some way, right? But again, if it's a small enough database, small size of the DAG, then it's possible. Uh, I don't have any practical production experience with storing a large structure, like tree kind of structure, or even a directed acyclic graph kind of a structure in the relational database. So yeah, not much production experience there. So
cool. Okay, I can take it up. Like, generally speaking, there are three very popular patterns to store any kind of hierarchical data, trees in particular. The first and the most common is your adjacency list, where you store the parent ID. Like if employee has a manager, then manager ID. That is the most common and the easiest and the simplest to set up. The biggest advantage in doing it that way is that data integrity is very easy to maintain. You know that there's a reference to a parent node, you have foreign key constraints, not null constraints, etc. And you can enforce your core domain model very easily. But as is famous, the problem with this approach is that querying becomes pretty critical. There is just no way to get all the nodes or children of a particular node without writing a recursive CT or a common table expression query. You cannot just write one single query that gives you everything. You have to go recursive, and then for a large data, even let's say about a million to two-digit million rows onwards, things start becoming a little slow, even with indexing, partitioning, etc. Once you go past that 20 million, 30 million range, the adjacency list starts slowing down. And if you are going to work on larger data than that, then it's going to cause performance bottlenecks. But if you know that whatever you're working with is not that big, then adjacency list is a pretty strong candidate. Because if you look at common use cases like categories, like there aren't those many categories in the world, right, to model.
Mm, mm,
So if you're let's say Flipkart, Amazon kind of thing, like maybe there are not enough categories to model that kind of data. And so when we are in the early stages of the product or early stages of the schema design, that whole bounded queue, unbounded queue design choice, we need to look at carefully. Like how big can the data grow? And then let's say one good heuristic is if the data is system generated, then we know the limits of data and then we can take a very strong guess. Like it's all the categories are going to be generated by let's say the admins of the company or product, then
mm,
you know that there's a certain limit to how big that can grow. But then if it's going to be user contributed, then you know that it has a potential to grow beyond any kind of bounds that you may think of in the beginning. And so that's the kind of thumb rule I generally use. If it's user generated, I avoid using adjacency lists just because the unbounded growth of that particular data is pretty high. But anyway, summarizing the adjacency list where you store the reference ID of the parent column is good for data integrity, but not so good for performance above a certain limit. Aditya, any inputs on this one? Like otherwise, we can go into L-tree and nested set. Those are the other two.
So one small optimization you can do over there. I mean, again, before all of this, I always say that start with the simplest thing and optimize only later because I mean nowadays SQL engines have become really good at optimizing these kind of things. But within that also one like mini optimization you can do is just have the uh, parent ID or the recursive references have a table just for that and like normalize your table out for the rest of the data so that those queries also can become much faster. And then after you have gotten your IDs from the primary query, then you can do a join for the rest of the data.
Yeah, I agree. I mean, working with sets basically is first class in Postgres, MySQL, and all the relational tables. And if you get a result set as IDs, you can use it in various ways. I think this is a very underrated strategy. I use it all the time. Because index lookups are so fast and integer index is again like extremely optimized. That is a very, very nice strategy, especially if you're working with any sort of large data set. Postgres is ridiculously good at working with a group of integers. Only seconded. Cool. Then the second one I want to address on this is the popular L-tree plugin. It started as a community plugin. It has since become like a de facto extension. I don't know if it's officially managed by the Postgres committee. I'll have to look that up. But L-tree is a very popular and available and well-maintained plugin. It still gets routine commits, issues, pull requests, all of that. It show basically that this data pattern is called enumerated path, where if you have a node that is, let's say, C child of B child of A, then A/B/C. You store that, and then L-tree goes on, adds some optimizations on top of that string-based path. And so inserting, deleting, etc. becomes easy. Querying is easy. You can make like search queries on string, starting with B, ending with a wildcard character, etc. or queries like tree depth become pretty easy. You count the number of path items, things like that. So it makes a lot of querying easier by doing some pre-processing on your path. So in my opinion, like, and in my personal use, that has become like sort of the best middle ground. And of course, the part where it falls apart is if your tree is really deep instead of wide, then you run into like readability and other issues. And of course, your index sizes can grow really out of hand because you're using inverted indexes and B-tree, and for your core lookups, you're looking B-tree index on a binary text column. And so if your text size increases beyond a certain size, uh, then again you run into index sizing issues. So there are obviously upper bound issues with the L-tree plugin, but still it's a pretty strong alternative to adjacency list, especially when used uh, on low depth trees. Any experience from either of you on L-tree
No,
or
I have.
any problems that you might see? Like, yeah.
Yeah, I mean, I haven't used it, but I mean, I always thought that, like you said, when it comes to querying, it's essentially a scan of a string. And like, I'm not sure how that will compare even with a adjacency list
No, so I
integer.
think what L-tree does is it has a string as a representation of the data, but it does store it in a more optimal fashion.
Okay.
So it allows you to manipulate the path as a string, but internally it will maintain it's like JSON basically. JSON
Okay.
will allow you to maintain JSON B. JSON B will allow you to maintain a JSON looking column, but internally it will have optimized representation of the data. So in that way, like L-tree works really well. If anybody like from the audience has a question on L-tree, feel free to post it. I'm actually not looking at YouTube. And Animesh, anybody from our team looking at YouTube?
Yes, I'm looking at the YouTube thing. No such question. I'm not seeing any questions about L-trees at least right now. But
Okay.
I think they will keep on coming. Actually, I had a question about database like data integrity with entries, like how and like if it's uh, storing it as a string, like how does that
Yeah,
affect?
that's a great question because honestly, I think with L-tree, no easy way to ensure that if A, B, C is in your path, then B must be present in the table. And with L-tree, that kind of integrity is not possible. It offers like some functions on top to do like lookups. So you could set up like check constraints otherwise. But off the like out of the box, it doesn't offer any integrity constraints the way adjacency list does. But because it
Uh,
is built for like performance and ease of lookup and ease of use, uh, the integrity part is a little bit left to the implementer. You could use
Mm,
it like.
no, just had a wild thought. I mean, why not do both L-tree and adjacency column and get the best of the both worlds depending on what your query patterns are?
True, I agree. And again, like the part of where you maintain the referential integrity can be handled by adjacency list. At least, like like if this child or node leaf record is in the database, it has a associated parent record, or it's a root record. And then you can also have like uniqueness constraints on how many roots you want to allow and things like that. And then L-tree for like fast processing,
Yeah,
which
I
actually brings
mean,
me to. Mhm.
in this case, I think you'll pay a penalty during inserts. But
And
generally, if like all the use cases I've seen, it's not a like for hierarchical models, the insert performance. I mean, it's not the
yeah,
requirement is not that high anyway.
correct.
But like hierarchies don't build up like in large numbers very quickly.
Correct. I think, and that's the working assumption. Speaking about inserts, like one of my popular thumb rule is like think of a car reversing into parking. If you're reversing a car and you're taking out, no matter how much effort you take, it's one time. Like if you take a lot of effort while parking the car, your taking out is going to be easy. Or if you park it easily, then taking out is going to be hard. But either way, you're doing a 1-to-1 ratio. and so optimizations don't matter. And so if we start extending that metaphor to like say 1 to 100, 1 to 10,000 beyond, a lot of these things, design patterns become obvious. Like, hey, how much work am I going to do? Which actually brings me to the next one, which is a less known uh, pattern called nested set. It's a data structure where you represent your hierarchy as nested sets. Those who are completely new to it, feel free to open up Wikipedia and take a look. But basically, you store left and right uh, numbers of your nested set. It has a diagram. Let me see if I can draw the diagram and show. Or maybe we can show it on Wikipedia. Wikipedia has a nice diagram.
I think we should also, there are some other questions around migrations and indexes, etc. So,
Nice. Where are these questions? I'm
should,
not seeing. Okay.
so one, yeah, on YouTube, I see one. Animesh, do you want to kind of read out or should I go ahead?
Yeah, I can do that. So I'll start from the top. So Anil has some. Anil has a question. So with all AI advancements, the migration on large tables and schema or index modifications are still a pain for me, he says. And the team expects zero runtime deployment without additional infra and online. Oh, I think that question. Okay. Also in hybrid use case of reporting slash analytical queries in OLTP databases, where the requirement is to hold the data for like a year or so. He asks how to uh, gauge the volume, data size, and network time for the queries.
So that was a pretty large question. Can you just copy paste it in the chat so that
Yeah, actually, I think
maybe
he's,
easier to read?
yeah, I'll just do that.
Yeah, I think we can break it down into almost like a data migration,
Mm,
schema migration for tables, index modifications, etc. And then separate is the reporting analytics use case.
yes. So I posted it on the group chat. Let me know if it's visible.
I can't like what is the link of AI advancement here? Like that, I'm not able to figure out like how does AI advancement really fit in here? But maybe Chinmay, do you want to? I think you have done a lot of large scale data migrations recently. Do you want
Yeah,
to?
yeah. So,
So I
yes, I
just
can
want to
take a
clarify one thing. Over here, are we talking about data migrations or schema migrations?
schema looks like to me more than a data migration.
Okay.
But yeah, I can talk about schema migrations, especially in like one of the specific DB use case, because again, would be to like best way to do this would be to read the docs and see try it out on staging environments and whatnot. Uh, so MySQL in one case I can talk about real quick. It was a real world use case that we had implemented where by default like MySQL 5.7, especially at least 5.7, it does online DDL kind of modification for schema, but then that will cause replication lags. And if you are someone, if you're running an application which you can't afford a replication lag and you have a very large data set, like in our case, it was 400 million rows in a table, growing a few million every month or so. So in that case, we ended up using a sort of third-party tool, which is either like there are two options in case of MySQL. One is the Percona toolkit. Uh, Actually, three. Yeah, one is called Percona toolkit. Other is a FB Facebook's OSC tool. All of these are open source online schema migration tool from Facebook. And one is that we use with GitHub's Ghost, which is again online schema migration tool. What it essentially does is it does a shadow table where it creates a new table from scratch with a migrated schema and then copies the data over from the existing table. And then at the last moment, it will do a switch flip, where it almost like acts like a rename of a table, right? So again, Postgres handles it differently, I guess. This problem doesn't really occur on Postgres in some way because of the way I guess it's designed internally and how it works. But in case of MySQL, these are some tools. One thing that the question doesn't mention, which I quickly want to point out, is how do you do schema changes, right? For example, you would always do backward compatible schema changes. What does that mean? For example, you accidentally started with an integer column for your phone numbers. for whatever reason, and you want to move it to a string, right? Don't just rename the column to string and then don't do it that way. Better would be to kind of have a new column, copy the data over, make sure all the data is in sync. Once, like, modify your application to use the new column, stop using the old column, and then kind of drop the column later, right? So you want to make sure that if you have to roll back, you don't really want to, or you shouldn't have to roll back a lot of DB schema migration changes, right? That's where kind of do the migrations in a forward manner where they are backward compatible always. Yeah, I think
I think
that is about,
I
yeah.
want to add one more thing to this backward compatibility, specifically in relation with migrations. So there is a concept called housekeeping or bookkeeping columns, which is used all the time in migrations. It's an old concept from signal processing called parity bits, or adding redundant information to make checking for faults easy. So one example is, let's say you're splitting a one-to-one relationship into a one-to-many, right? Let's say you have a comment belongs to article, and now you want to change it like comment an article, like the one comment can be multiple articles, right? I know, bad use case. I picked it right off the top of my head, but imagine that, like, you have a belongs to relationship with a foreign key reference in your table, and now you want to change it to a join table, and you have already enough data in production. You're migrating over. One of the things to do is keep track of the old ID into the new table, and enforce, like, what are your invariants, like if this ID with this particular article can exist, and if you run the process the next time, you don't want to create multiple records, for example. So you add the reference to the old ID until your migration is done, and then when your migration is done, you can remove those IDs. So things like that. So these kind of bookkeeping columns of housekeeping techniques, basically they speak to two things. One is the invariants in your data model, which are key whenever you're doing any kind of schema changes, right? Even, let's say, even if your schema is changing, which means typically either your domain is changing or you are changing it because maybe performance or some other application related reasons. For either case, like, let's say even if your domain is changing, there are some things that won't change, and it's critical during a migration to lock in those things that don't change, and add like counters, like number of, like, basically counts and things like that, to make sure that you don't mess up, because item potency otherwise is very hard to achieve. And generally speaking, for any kind of schema migrations or even data migrations, item potency is the key design principle that is going to uh, make sure that you run it with a fault tolerant approach. Housekeeping column is just one of the ways we do. The other, specifically when it comes to data migration, the other strategy I use is the growth rate of tables. This is something I've personally done multiple times. We were doing a pretty large data migration. We were moving data from Neo4j to Postgres, and we already had like around triple digit number of records in around three tables, which were our core tables. And so we were splitting that, and we are moving into new DBs. In phase one and phase two, we changed the primary key from UUID to integer, because it was easier to maintain polymorphic associations with integers. And so when we were doing that, there were a lot of complex joins, and we had to untangle uh, our core data. And when running the migration, one of the things that kept the migration in check was we were looking at growth rate. If you're migrating two tables with, let's say, 10 million rows each into, let's say, four new tables, then how many records should you have before and after the migration? And does your growth rate, as you're running the migration, it takes a couple of hours to finish. During your migration, like, what are the row counts checked periodically? And if that growth rate of the columns looks to be accurate, then you are on track. Otherwise, you need to change your strategy, etc. So a lot of these housekeeping principles and parity bits basically came in useful. So that's one. This is a strategy I use for all schema and data migrations. Like, just add a lot of redundancy so that you can rerun the thing again, and you're not worried about, oh,
Mm.
if the server crashes, whatever timeouts happen, you're not in for a bad or corrupted data state.
Yeah, I have a couple of points to add to that. So For example, Chinmay mentioned that you have having backward compatible migrations is important because you also need to be able to roll back and all. But one thing you have to also remember is that nowadays when we are deploying in cloud environments, which is almost always the case, that you have multiple applications and multiple application nodes. So even when your deployment is going on, remember there are two versions of applications that is running till the deployment is complete, right? The old one and the new one. So if you don't have backward compatible schema migrations, what's going to happen is that, I mean, not only are you not going to be able to roll back if something goes wrong, you're going to have a time period during the deployment where data inconsistencies can creep in, right? So it is like almost a mandatory design decision when you do schemas. The second thing is that you can't really talk about schema migrations independently of the application versions as well. Right? For example, if you want to drop a column cleanly without any downtime or without any data inconsistency, it's actually a process of three releases that you need to do. One is where you stop using the column. One is where you make the column read only. Second is where you stop using the column deprecated, and the third is where you drop it. So to completely drop a column, for example, it's a sequence of three releases that you need to do. To update a column, it's four, right? So that is an important point to remember, something that I see is ignored a lot, and then it comes to bite you when you're actually doing your deployments.
One small tactical addition I want to add. There is a really nice in the Ruby on Rails world. There is a nice gem called Strong Migrations. It uses a lot of these principles and compiles them in a nice gem. So if you're running a Ruby on Rails app and if you try to do an unsafe migration, which for example, let's say renames column and all, then it goes and fails the migration during development time. And so, but let's say even if you're not in the Rails world, you can look at the wiki of all the things Strong Migrations maintains and make sure like when you're running your migrations, you have a check for, okay, if I'm doing this, then I need to rethink it or at least have strategies in place to avoid things. Rename column, I think, is one of the like the easiest trap to fall into.
Yeah. If people are interested in this, then there is a really good book that I would recommend. It's pretty old, like 2006 it was written, called Refactoring Databases, Evolutionary Database Design, where it's written by Scott Ambler and Pramod Sidalagi. So it goes into the whole structure, refactoring, data quality, referential integrity, column renames, any architectural changes, all of that in detail. So that's pretty useful. I keep referring to it if I'm dealing with some interesting, challenging problem.
Nice. Cool. I think there is a JSON related question from
There's
actually
one about performance in hybrid use cases of reporting analytical queries in OLTP, where the requirements is to hold 1 year data in hot store. How to gauge the volume of data size and network time to render?
I think it's
I
mentioned to
don't
the
understand. So volume of data, understand. I'm not sure what the meaning of network time to render is. But I
I
mean,
think that's for the carrier part, as in uh, when you're making the request to this database, that incurs a network request most likely, right? If your database server is not uh, co-located. So I
mhm.
think that's what he meant.
Okay. So I mean, this is mainly about sizing and performance. See, when it comes to databases, there is no that there cannot be any theoretical formula because it completely depends on the nature of data, right? So my only suggestion is to keep measuring and extrapolating. That's the only thing you can do.
I think there was an element of question about OLTP or analytical type of database. Famously, like relational databases have been bad at running analytical queries because you need a column-oriented lookups in analytic style, and which is why you see like an explosion of at least columnar data stores or column like bigger databases like which handle like BigQuery and what is that Amazon database columnar? I forgot. I'm blanking out on the
Aurora.
name. Or
Red,
no, no, Aurora is your
Redshift, I
database.
think, is
Red.
Yeah,
yeah.
Redshift, Redshift and Bigtable in around. Uh, After a certain volume, like Postgres becomes a little bit useless for analytical queries because you need to add a lot of indexes and all those things, which are going to cause your transactional parts of your app to become slow, and it's generally easier to separate them out. I think the question was about like how do you gauge the hot store and volume? Okay, let me address this. I think I sort of understood what they're trying to ask. One common pattern in analytical stores is you create and store snapshots of data. Your transactional data is a live database that updates as and when your application operates. In OLTP or analytical databases, you take snapshots like every Saturday, every day, every month, etc. Because then you plot the progress of a particular column. Let's say number of articles today, next week, the week after that, etc. And so these kind of queries are not possible to do in a what do you say modifying or mutating database, and transactional databases are typically mutable databases. Like if you have a number of article count, Postgres or MySQL is not going to keep a track of how many articles were there yesterday versus today, right? It's going to guarantee that if you insert an article, it's going to be in the database. So different guarantees. And so if you have that kind of snapshot, then the straightforward back of the envelope calculations are about your growth size and the frequency of your updates. You just can plot like a basic graph to see how your growth looks like, and then do calculations accordingly. Like in my opinion, that there is not a lot of more to it other than just the frequency of your backups and the growth rate of your actual transactional data.
One point that I can add, this is kind of related to one use case that we had, but I believe like many of the folks may have similar use case. So typically you would start with one database, right? Like no, not even primary, secondary, replica, etc. You have one database, which is OLTP, where you're also running some basic simple queries, right? That's how mostly things start. The next thing, how you can do, you don't have to really add a columnar storage at that point. Like what we had done and what I've seen worked well for us is that we first added multiple databases, as in that we basically had a read-write split. So you would have a primary writer where all the write queries would go, all the read queries would go to the replicas, right? And some of my analytics queries would also go to any of the replicas. That was still working pretty well. After a point, what we did is we added a specific read replica purely for analytics read queries. So we would call it analytics read replica, right? Where all the analytics queries would go into that machine, and we would try to scale that bigger and bigger still not going columnar way. Came a point later where we would then have a columnar database, like we would do a migration in some way where we would do BigQuery or Redshift or even ClickHouse or whatever, right? Whichever you want to go for. And that's where you would then go and move all your queries into a columnar database. Then at that point, you would have to kind of worry about and think about a data sync. Like, do you want real time or close to real time data sync? Do you want to have a sync every 24 hours, every 1 hour, every 15 minutes? What really depends on the business or whatever use case. But a pure transition from like one database, multiple database, read, write, split, then analytics read replica, and then finally a columnar storage is what I've seen helps you deal with the scale and the growth in linear fashion typically. I haven't found or I haven't worked on use cases where one fine day there was like a, let's say, gigabytes of data in the database, and the next morning we blew up in terms of usage and multiple gigabytes started coming in per day, right? It doesn't happen like that unless it's a very viral kind of growth. So in most cases, going this like step by step route kind of made sense purely from scaling the application and dealing with and changing habits of people and whatnot. So that I found pretty useful and pretty practical for most use cases.
Nice. That's a good step-by-step breakdown of the analytical database strategy. One pattern we used in Colon and was very useful. Uh, we later abandoned it because the prices started getting out of hand. We were like doing aggressive cost cutting. But basically we had a service-oriented architecture with multiple different databases, services owning their own each writable database, and then each service and by virtue each team was responsible for publishing like every Saturday or every Friday on their own cadence of the current state of the database into our AWS storage. And then we had like Athena and a bunch of other query builders, CSV processors on top of that, who would put it in that storage. And then there was a final Athena based query engine that we would run. And so this pattern, basically the only thing or the biggest advantage this gives over your traditional setting up views or read write replica is that you can chart the progress of a column, over time, which is not possible with having read and write replicas. You want progression of a column, progression of relations, how things happen. Then this kind of analytic tool, this is the only way to do it. Typically on a product and business level, teams use a tool like Mixpanel, where you keep posting events, and then you have these time series charts of things, how things progress over time. But we are not really used to doing it in our core application data, and mostly because we don't really need it that often. But there are times when you do need it. Like we were doing like attendance tracking, timely reports, etc., messages sent to parents and things like that, which were pretty domain specific to us. And for every engineer on the team, looking at the progress of how that relationship changed. And when I say relationship, I mean like relationship between the two columns or two tables. How that changed and evolved over time was very powerful. Like it influenced a lot of later design choices and decisions that we did. And so that's a pretty popular pattern. I think the question OP asked sounded very relevant from that perspective, where you have a continuously growing analytics database, because there are two growing factors. One is your time. You are doing a dump let's say every Saturday, but your primary database is also growing, right? So 10 GB to 15 GB. So you have a sublinear or sorry, polynomial rate of increase. And so then it becomes pretty hard to manage, because at some point, even though our core database was, let's say, a couple of hundreds of GBs, our analytics database was like terabytes, multi-terabytes, and going closer to petabytes. So then that's a hard problem to solve. And the only way to solve it is like keep like a rolling window of, let's say, only last 6 months, and then dump everything beyond whatever is last 6 months. So you keep like a window, and that controls your total size of the database, because you can't control the rate of growth. That is on your core application. You can't control how your application data grows, but you can control how much you store. And so those are the two levers for us to move. Okay, I think let's move.
So, yeah, I think move on to the next question. Um, so, what are the thoughts on storing basically columns? Is the question. Like, so OP thinks that it's pretty counterintuitive, and it is against the relational design principles. Anyone has thoughts on that?
Yeah, I mean, see, it all depends on your domain data model. Right? So, okay, let's go a minute into schema-less versus schema based design, right? When you talk about schema-less, I've seen two scenarios. One is where your domain itself is schema-less. An example I can give is, for example, you have a flexible form builder where users can add fields and other users can give answers to those fields when they're filling the form. As a designer of the application, you have no idea what the fields are going to be that one user creates and the other is going. So you don't know what the schema is in that case. So it is truly a case where the schema doesn't exist when you're designing the application. The second is the schema exists, but for whatever time, resource constraint, etc., you don't really have the resources to actually think about the schema while you're doing the development. That I strongly discourage, because it is going to come back later to bite you. So it's always worth putting in that effort upfront. Now, when you actually have a scenario where your domain itself doesn't have a schema, in that case, I always go for JSON columns because that's the best way to map a schema-less component of your otherwise uh, properly structured schema. And in that sense, it doesn't feel non-intuitive to me because you are accurately representing what the domain model is. I mean, that's what relational modeling is about, or any database modeling is about. You're trying to as accurately represent your domain model, right? And obviously you have to make optimizations like normalization, etc., which may not exist in the domain model for efficiency purposes. But as long as what your database design is in accordance with what's actually out there in the domain, I think it's fine. It doesn't seem non-intuitive to me at all.
I agree. I think JSON is not a replacement for developer laziness, but if it's part of the domain, then it is part of the domain. And the great thing is Postgres, MySQL, SQL Server, all of them have a lot of advanced functions, check constraints, everything on JSON columns for you to maintain that core domain data integrity invariants. So even if you have a JSON B or a JSON column, you can add, okay, it must have these keys. You can add a little bit of loose schema on top of JSON if it needs. Like let's say you are adding like custom fields or some sort of dynamically generated pairs and you don't want to do a very sophisticated NetSuite style deep schema. You want to keep it simple with JSON. uh, you can add like, okay, these keys must be present, these values must be present, things like that. This value cannot grow to a size bigger than that, etc. So there are like different like check constraints, uh, indexes you can do to make sure that you have a minimal integrity layer constraint checking on top of your JSON columns. So in that sense, like usually don't shy away from JSON columns. If they are part of the domain, then they should be there.
Yeah,
Yeah.
another aspect to think about when you're designing this is what is the read pattern? Like for example, if your whatever you're storing in the JSON column is anyway going to be read back as a single unit, then JSON column definitely makes sense. See, the other option is to create a table of fields, another table of columns which refer to the fields and so on. But if every time you're accessing the data, it is going to come back, you have to access it as an object anyway, then breaking it up into two tables of fields and values with references, that actually to me is non-intuitive with respect to the domain model.
Yeah, totally. I think I can give one example of a practical use case where we use this, and this kind of combines a bunch of principles or thoughts that both Swanand and Aditya has talked about. Is there was a app where we were doing CVE analysis, the common vulnerability analysis, and you would do some checks somewhere. There's a bunch of structured data in terms of what assets these are called typically, where you are checking the CV against, etc. So there's a lot of structured data which is in Postgres, and if there is a match, then you have a bunch of metadata that you get. Now, what that metadata is different based on type of CV. So we don't know. It can be very dynamic, right? So what we ended up doing was just for that particular data, it was stored in the JSON B column. And even on the UI, when you render, you would want to, as Aditya said, if you want to read the entire column, that is exactly what our use case was, where all of that data we would read and we would just show it as a tabular format key value pairs in JSON, right? So that's a very classic use case for that kind of use case where the domain, some part of the domain is relational and some part we don't know the schema where whatever could be there, whatever works. So in that case, having a JSON B is like a very good use case in that way.
Cool. But yeah, like don't shy away from JSON columns, especially JSON B. Like fairly performant, easy to use, and easy to check and add constraints and integrity on. But it should never be used as a replacement for developer. Oh, I don't want to design schema is very different from my schema is loose. And I think this is one of the reasons, like popular reasons why MongoDB became so uh, ubiquitous, is that it was just so easy and lazy to starts the database where you did not have to define any columns. But there's a lot of advantage in uh, doing a schema. One, again, like a meta tactic or strategy is that doing your relation or designing your schema forces you to also design your domain, and it leads to not only your like good database and good data integrity, but also to better code. Like good domain modeling is a key to writing applications that stay robust. And so in many ways, like Postgres and MySQL, they force you to get in and do that upfront thinking about your domain, which otherwise you may or may not do. Like especially like early stage startups where engineering rigor and all is not always seen as the most important thing. It's easy to give in to the iteration speed without really putting in the thought. Uh, And in my opinion, like Postgres or any relational database, it adds that responsibility to you in the beginning, and it's a good thing. Like small friction upfront for avoiding like major problems down the line. And that's how I look at it. Yeah.
Yeah, no, and there are a couple of quotes that encapsulate this concept very well. I mean, not from like there's one from Linus Torvalds who says bad developers worry about code, good developers worry about data structures and their relationships. And there's another, I don't remember who it is from, but basically it goes along the lines of uh, show me your code and hide your data structures, and I'll have no idea what this is doing. But show me your data structures, and it'll be obvious to me what your code is.
Code is totally agree. Yeah. And then
Yeah, 100%.
another wise quote from me. uh, it says weeks of working can save you hours of planning, right? Which means you better to like the advanced planning is so awkward and sometimes tedious. The 3 4 hour activity that we end up foregoing it only to put in like weeks of work in order to hide our bad design choices or get around our bad design choices. It's true for all work, but very specifically with schema because very difficult to change things later in a way that is neat and clean. Cool. I think there are a couple of interesting questions about clustered indexes and all. Let's go to some of those. I'm just going to scroll up.
Clustered
And so
index is
once
the, sorry, I'm a bit out of touch. That's the sequential index, right?
Correct. So clustered index is where your data is stored as per your index. Usually, like your data row, like the way you store your data and indexes will be separate. That's the default mode in Postgres and MySQL. But you can make Postgres and MySQL store the data as its index. I think it's a pretty nice segue into some of the different design choices. I'll quickly add a couple of thoughts and then Chinmay, Aditya, I would love to hear your experience on clustering. One common and the most uh, ubiquitous pattern and use case for clustered index is your standard B2B SaaS model, where your data is multi-tenant in nature, and your access pattern for data are always around either a single column or a single or type of column or type of rows. Like let's say Gumroad, for example, right? So you're building something like Gumroad, and you are never going to need to look at let's say Aditya is a creator on Gumroad and Chinmay is a creator. You don't ever need to look at their data together, right? Only in analytics store you need. And so your fragmentation is at that business level. Now, obviously, multi-tenant, I'm not going into deeper aspects of multi-tenancy, but even for non-multi-tenanted data, when you're working on batch data, like large volumes of rows together, clustered indexes are incredibly useful because what happens is like you do an index scan and all your data is in that same page on the hard disk or a similar location on a hard disk. And so Postgres in particular, I know how Postgres operates. MySQL, I don't know, but I can look it up. Postgres keeps track of like where your data starts and what rows are stored where. And so your batch lookup and data transfer becomes like an order of magnitude or even more than that faster, just because your data is stored sequentially as per your index ordering. So let's say you have a primary key or business ID and some article ID or something or product ID. then all the products are or items on the product are stored in that order. And so queries like give me all the items or all the products for this business becomes a straightforward fast query where you can just get a chunk of data from the database in one shot. And so the main design choice for clustered versus unclustered is your reading patterns, because clustered indexes do a lot of work on the write. So if your read write ratio is very high, then, and when I say high, generally means anything below 1 to 100. 1 is to 100 is considered high. 1 is to 10 is considered extremely high. So if basically 1 is to 10 is like 10 reads for every write, and 1 is to 100 is 100 reads for every write. So if you're anything between that, that is a fairly high read write ratio. And for a high write database, clustered indexes can cause a lot of slowness on insert, because they have to do a lot of work every time your insert comes. If there is a data on particular size, it needs to be moved around, a lot of housekeeping needs to be done, columns need to be updated, etc. So Postgres does a lot of work during indexing. And so if your write ratio is very high, but your read patterns are like you need clustered reading, then you are in for a little bit of a soup. And then you might want to change, like, or do some other strategies, change your schema differently. But let's say we are operating at a reasonable read write ratio. Clustered indexes can give incredibly strong performance boosts for reading batch data, like multiple records at the same time. Please note that there is no performance gain for single row lookup for clustered data. Usually, if you're doing like a double, let's say business ID, product ID, then obviously clustered index, even there, it has performance gains. One really, really nice use case to read upon this is Shopify's recent switch to using composite primary keys to get around this exact problem. They ran into problems where even clustered indexes were not enough for them. So they had to switch to like composite primary keys. And they have written a pretty detailed write-up on this, which goes into a lot of design choices and performance optimizations about clustered reading. So Divya, I hope that answers your question.
So
Yeah.
I look at it slightly differently, almost like a special case of what Swanand said, and that is when your read and write patterns are primarily around ordered data. When there is a notion of order or sequence to your writes as well, and when you're reading data, you are like reading from this to this, like timestamp based index or something like that. And that is where clustered indexes will give you the most uh, optimum performance. It's almost like you're heading slightly into the domain of columnar databases. And if that is your use case, but you don't really need a full-fledged columnar database, a clustered index is like a good middle ground, at least to start off with.
Yeah, Aditya, just one quick addition to that. They are also pretty good with group data, not just ordered. So within the group, if even if you're not ordered or if you don't specifically need order data, if you have a batch of, let's say you're tracking student attendance per teacher, right? And so then if you have a clustered index based on a teacher and student ID, then it makes it very easy and performant to get like all the students of that teacher. Within that teacher, like the student ID or ordering might be different, but the grouping and batching, that is the one that is the target problem for the clustered index use case. And it's actually like, because it's not taught and discussed quite often, uh, a lot of developers don't even know. Like for example, Rails and Django did not have a way to specify that this index should be clustered uh, until like very recent versions, right? So it's not very common practice, and a lot of developers don't know about it. But it is a pretty useful performance pattern, specifically if you're using like very heavily like domain heavy data where lots of foreign key relations are present, and then you have large tables based on those relationships. Super useful. Chinmay, you were saying something when I cut you off.
No, I think nothing much to add on the cluster side. Generally, again, for the indexes, I just posted on chat also. There's a interesting thing, that rabbit hole that I went down into. There's a website called Use the Index Look. It talks about like everything about indexing that you would ever want to know almost. So really good website. So do check it out.
Yep, very
There's a
famous.
question, I think, from Anil on the career path.
Actually,
So
before
I
we go
guess,
there, I just want to check with Divya whether her question is answered, and do you want to hear
yeah,
anything?
Yeah, so thanks, guys. Actually, this is very helpful. I just had one follow-up thing. Like if I have to like have multiple indexes, so there's only one clustered index, is what I understand, and the rest have to be the non-clustered indexes, right? So,
Correct.
like how do you choose between those two? Like, which one is that I should go for the clustered, and which one's that I should go for the non-clustered?
So the most intuitive answer is that you choose based on your read patterns. But I like to stay close to domain more than that. Like in your domain, what is the true representation of that cluster? Like what is your core grouping strategy for your data? And I personally prefer to create cluster indexes on that because invariably as the application progresses over time, your read patterns are clustered and centered, no pun intended, around that core domain relationship. Uh, in the shorter term, in the early stages of product, it's possible that your read patterns are different from your core domain. But as things stabilize over time, and this time is different for each product, they become centered around your core domain model. And the good thing is, like in Postgres specifically, you can change the cluster column later, but you just can't have the same cluster index on two columns at the same time. But you can migrate and change data later. So you can choose to do something on the current read patterns and the near future read patterns, and then in the future can change it. Although like that migration, if you have over 20, 25, 30 million rows, the clustering can take a long time. Especially the one thing to consider if you are changing your clustering index is the disk size available. If your disk is operating at like anything more than 50% capacity, the clustering or reclustering can be very, very slow, especially if the database is in currently use. And so these are again like more details than you asked for, but you don't have to be locked into a particular index. You can change it if you want to. But if you, let's say, if you're in a position where you are not able to change it, my advice is to keep it as close to the core domain as possible.
Yeah, that's helpful, Swan. Thank you so much.
Okay, Chinmay, what should we tackle next?
There's one on career as where was that one?
yeah, as a database engineer, like what's the growth path in career, and how do you how do you keep up when you get multiple databases introduced for various different use cases, and there is so much, I'm guessing, marketing on the website that hey, we are the XYZ replacement, we are going to change the world. That kind of marketing, I'm sure, that gets a lot of people restless. How does one keep up with day to day and adjacent work? Do you
So
want to take it up,
just
Anand?
I,
yeah, just one note. I think we're getting close to like we're reaching the end of the time. So this might be the last question. So yeah,
so I would say there are two parts to this when you say database engineer, right? One is the whole admin side of it and performance side of it. And that is very specific to every database engine and new database model. And over there, I mean, you just have to repeat all the work that you have done uh, for the earlier databases that you are familiar and good at. The second part is the whole database modeling aspect of it. And there I would say that the best way to kind of keep up is to go back to CS fundamentals. Because at the end of the day, all data modeling is based on the same principles of data structures, algorithms, runtime complexity, all like finally it boils down to that because other than the actual nitty-gritties of storage optimization, etc., and databases, it's all about data structures and read and write performance, right? So, for example, if you look at a relational database versus a columnar database, it's just a different data structure with different trade-offs that they've chosen. And based on those trade-offs, you're going to get different performance characteristics. So if you have a good grasp of the fundamentals of computer science algorithms, I think it will be much easier to keep up with. So basically, when a new database comes or a new data model comes, or you see some new marketing material out there, you can quickly go and map it to some earlier concept that you know, and you already know what the trade-offs are. And then you can just quickly decide, okay, is this a good database for this particular problem statement?
That's actually a pretty comprehensive answer. Animesh, I hope you're taking notes. There is a really interesting question from Abhinandan, and it has an interesting answer, so I want to go into that. So let me quickly read that question. So he asks, any tips to improve read replica resource utilization, like preventing large CPU spikes and huge replication lags when a large number of deletes are happening on the primary DB? In a definite time period, right? So basically, he's asking if there's a migration going on, deletes are going on, and then read replicas can actually become slow. Uh, so the answer to this is multi-layered, and I would say like both Postgres and MySQL docs go into depth of when the deletes are happening, how indexes operate, especially running concurrent indexes. But the design principle that I wanted to answer was the relationship between the penalty you will pay and the utilization of your resources is non-linear. And what I mean to say is, if you're the more your percentage utilization of your resources, the higher penalties you're going to pay. So if you have a database, let's say that has 72 gigabytes of memory, and you're operating at 60 gigabytes, and something like this happens, you're going to pay a much higher cost and delay than, let's say, if you're operating at, let's say, 32, 34 GB, like 50% utilization mark. Right? So your percent utilization of your resources versus the lags that you will see is non-linear, right? It increases as you go towards 70, 80, 90. And so if you want to avoid large CPU spikes, then number one thing you need to look at is your utilization of your resources. If you have low util, then you can get by some of these things very easily, or at least without large spikes. Basically, this is your core queuing theory. If you on low util, you end up paying low price. So that's what you want to Vinandan, that's the one part you want to anchor on, is that if you're running a large scale migration, do it at the lowest traffic period and lowest utilization period, because that's when you'll pay the lowest penalty.
Thanks, Anand, for the great answer. So what about like regular DB purges? Then also we have a large number of deletes on the primary, right?
Got it. So one way to look at it is that 100% uptime is highly overrated. If you can take like a maintenance window, then do these activities in a maintenance window. Very few apps in the world need to be up all the time. So if your app it has the luxury of, let's say, Saturday night 1 a.m. whatever, in your core or the most median user database, you can take a downtime. Then my recommendation is take the downtime and do it. Right. But let's say if you're in a position to where you absolutely cannot take it downtime and you want to purge the data, then generally speaking, I prefer moving the data first and then purging it. Aditya spoke about the three part approach to making a irreversible decision on database, right? You first stop using it, whatever, like then use the new thing, stop using it, and finally delete. And so you have to use that three-phase kind of approach even when you're doing data purges. And I'm assuming you're asking about data purges from my data size is going too big, I want to reduce it to reduce operating costs kind of perspective, right?
Yeah, sure. Yeah, that's
Yeah. Yeah, because we used to do that in Colon. We wanted to bring down our database costs. And when we did a deep dive on cost, we realized that a lot of the costs are from the size, and the size is coming from index size. And then the index size is big because the table has grown so big, but we are not using any data before, let's say, June 2021. So why have it around and keep the data size large, where you can keep running leaner operations? And so it's a common need. But my recommendation is that just do it when you can take a downtime. That's the least hassle way of doing it.
Yeah, one more strategy you can apply, I'm not sure whether it's supported in all databases, is basically have a partition on your table and purge entire partitions. And so then what you can do is before the purge, you can just stop replication of a particular partition and then just purge that partition.
Yep,
Oh,
that's it.
that's really interesting. Yeah.
But I mean, your domain model should be such that that partitioning should be possible to begin with. But where it is, that's one strategy you can use.
The amount of time the word domain has come up in today's discussion should give a hint to everybody of like how critical staying close to the domain is and getting clarity on your domain. I think that is the number one pet peeve of mine. Like when I see database usages and anti patterns in the wild, is that you start straying wild from your domain. All the bad things happen. The distance between your design and your domain, it's like directly proportional to how many bad things happen in your database. The closer you are to the domain, like the fewer chances of you doing something egregiously wrong. Cool. I think there are a couple of other questions. I'm okay to extend it a little bit just to answer the questions. Like
Yeah, I can stay for another 6-7 minutes.
same.
Well,
Yeah.
Okay. Just scrolling up to see what questions are there. Do you advise sorting in database or sorting in application layer, considering app can scale better than DBs? That's a nice question.
I would say app can scale better than DBs is not a universal truth.
I agree.
So where scales better than your DB, sort it in the application.
Yeah. The
But
only I think my golden rule is avoid multiple trips if possible to the database, because
Yeah.
network versus in memory can make a lot of difference. But the sorting itself, I mean, universally we know like you cannot do better than n log n when it comes to sorting, right? There's no way to do better than that. And then databases are already faster, like they C and whatnot. I'm pretty sure like Postgres has more optimized sorting code than whatever you can write in your app.
yeah, and one thing you should not forget is that with all these modern database engines, caching is a big factor. So if the same table is being queried again and again with the same kind of select sorting, the database is likely going to outperform your application layer.
I agree. So yeah, so in my opinion, like just the only thing to optimize for is basically number of trips. So if you're sorting and fetching data in a way that is going to need multiple trips, then optimize on that. But the actual sorting itself, like I personally always prefer to do in database, unless there is enough evidence. Let's say in Neuralink or something where in our whatever observability tool we're using, that this can be done better on the app. I personally haven't seen the use case where app is scaling better than database, like or at least in terms of sorting. Maybe for like a billion row sort or something, perhaps, where the
Yeah. But
disks are
even I
not
think,
involved and Spark is sorting your stuff. Maybe in that
yeah.
case.
But even in the application case, if you are on some containerized or whatever workload, you're going to have multiple instances of the app, and you could do the sorting on a database on one instance on the database itself, whereas in the app you would all of the app instances would have to do the sort. If there is multiple queries at the same time and whatnot. That's how. Yeah. Again, that's another trade-off in terms of like one was the network round trips, other is how many times do you have to do it on the app and whatnot.
Cool. I think Chaitanya had a question with Aditya already answered. He says if the domain itself scales, and I assume by scaling he means change or evolve, then is a rational database in the first place a good choice? Or you might want to consider document store. I think we answered that. Aditya answered that earlier, where
Yeah, and see, in most cases, a thumb rule that I follow is use a relational database until it is proven by demonstration that it's not working. And when I say relational database,
Yeah.
I'm including all the modern facilities like JSON columns, etc., etc. So, like in most of the cases, when people say that, okay, a non-relational database is going to be better, I've found that they haven't really utilized all the facilities of the relational database before uh, making that choice.
Yep.
Yeah, that has been my bang
Agreed.
on, like very similar observation.
That reminds me, we agreed too much. Like, uh, maybe you should have added like if somebody like from the DynamoDB team or something. Like I think iScale is where a lot of things start changing when it comes to Postgres and MySQL. Specifically, my experience has been that once you are past billions of rows and hundreds of writes, let's say per second, hundreds of writes per minute, maybe with billions of rows. I think uh, if you're not careful about your schema, you start running into problems. But if you're like very careful with schema, like I have personally operated a database with like 3-digit billion number of rows with around hundreds of writes per second and with a single Postgres instance with a backup like failover. And it worked just well, like good enough. So that's my personal limit of how much I have done. Maybe Chinmay has done like
Yeah, and so see,
Yeah.
there are some trade-offs that you have to also consider. Like, for example, you're storing a lot of events that are coming from all of your end user devices. For me, I mean, using a separate database which is fine-tuned for very high write performance, but is an obvious choice over there. There you don't use relational databases, but then that's not really part of your domain model as such, right? It's a very specific analytics use case, and there are databases like Cassandra where who have taken different trade-offs for that particular use case. So in those situations, sure, you should go ahead and use those databases. And like, but I'll give you an example. If you're, I don't know whether this is available in Postgres, but if you look at MySQL, uh, you can actually configure certain tables to not have any of the ACID properties. And that, like the performance of that table will just like be far more than any other uh, table in your database. So even these options are available. But if you know, for example, that, okay, I'm going to go to like uh, 500,000 devices, each of them sending me a ping every 30 seconds, then if you're sure about that, then just go to something like Cassandra or something which is columnar.
yep.
I think
Cool.
there's
I
one
think
use case that I'm currently working on, which is around writing, having about 5 to 10,000 writes per second on a single Postgres table, and it just has like 4 or 5 columns, and it'll have about 50 million rows to start with, and it'll eventually go to like billions and continue to increase. There is a way to partition this data also in some way, and but yeah, that I'll keep you posted, and we can have a like I'll do a stress test on Postgres and see how it goes.
nice.
But
I mean, in
You
that case,
actually,
I'm guessing you're not defining any index on it, right?
right.
there is an index which is composite purely needed for the query part because we want to query uh, just those values, not the other two rows, other two columns. But yeah, that's again debatable. Like I'm thinking, how do we
Yeah, I
test
mean,
it, load test it, and see? Yeah,
yeah, I mean, one like first thing you would do to improve write throughput is drop the indexes and then have another table where you're copying or whatever
correct,
ACID
correct.
and
Correct.
have indexes over there.
Yeah, by the way, speaking of that, the row width is actually a pretty core design choice. Like it influences a lot of design. If you have like wide rows versus if you have small rows, that can change a lot of your domain design. Columnar databases, like for example, can't do much if your rows are very short, right? Like if you have like a 4 or 5 column, very heavily normalized design, then your analytics database is not going to perform any better than your Postgres.
Oh, far worse.
Far worse,
Yeah.
in fact. Exactly. Great. I think let's close on
All
this.
right.
I'm
Yeah.
sure like there are more questions, but there's no limit to how much we can talk on this. So maybe more questions come in, we can do like a follow up some other time.
Yeah, definitely. So if there's any more questions, feel free to just dump them on the comments page on the Hasgeek page. And I'd like to thank everyone who have joined and posted their questions on the Zoom call on YouTube and all. So thanks again, and thank you, Swanan, Aditya, and Chinmay for answering all of those questions, including mine. So it was pretty great to see you offline, and I hope to see you in person soon.
Yep. Thanks, everyone.
Sure, buy me a ticket,
Right.
like I'll be
Thanks.
there.
Bye. Yes.
Okay,
All right.
Right.
Bye.
Bye.
bye.